Thank you very much for the invitation. This is a joint work with Liang and Vasilis Syrgkanis. In this paper, we're going to study a dynamic learning model with limited resources. In our model, there is a decision maker who wants to learn an unknown state by aggregating multiple sources or kinds of information. Each of these sources provides Gaussian information about an attribute, and we assume that the payoff relevant state is a linear combination of these attributes. What makes the problem complicated but also more interesting is that the attributes may be correlated with each other, so that information about one attribute will also provide information about other correlated attributes. In our model, at each moment in time, the decision maker has a budget of attention to allocate across these different sources. And what we assume is that more attention devoted to a particular source will increase the precision of information obtained from that source. To conclude the model, we assume that the decision maker also decides when to stop acquiring information and take a decision. And what we want to do in the paper is to characterize the optimal path of attention allocation and also potentially say something about the optimal stopping time as well. So here are some examples that this model is meant to capture. As a first example, imagine that a mayor wants to estimate the number of COVID cases in the city. What he or she could do is to allocate a limited number of tests across different neighborhoods. More tests devoted to a particular neighborhood will increase the precision of knowledge about the incidence rate in that particular neighborhood. But because the mayor ultimately cares about the overall number of cases in the city, he wants to balance these test allocations across different neighborhoods. A different example is for an investor to learn about the value of a large portfolio that consists of different individual assets. In these situations, it may be difficult to assess the overall value of the portfolio directly, but the investor can acquire information about these individual assets. And finally, we can imagine a newsreader who reads different media sources to learn about, for example, a new policy proposal. These different news sources will come with their own ideological biases, so the newsreader have to aggregate different biased information across these sources. So here is a quick summary of the results in the paper. What we show is that under certain conditions, the optimal information acquisition strategy can be exactly characterized and has a simple structure that I'm going to describe to you later. The tractability of this solution and the model lends itself to various applications, a few of which we illustrate in the paper. In particular, we use this characterization of the optimal information acquisition strategy to derive new results and insights in 3 different economic settings, which I'm going to summarize toward the end of the talk. So without further ado, let me get into the model setup. In our model, as I said, there are going to be k unknown attributes, theta 1 through theta k, which I assume are fixed over time. There is a joint normal prior belief about these attributes with prior mean vector mu and prior covariance matrix sigma. Time is continuous, and at each instant, the decision maker is going to choose attention levels to devote to these different attributes. These attention levels have to be non-negative and add up to 1. There is going to be one information source for learning each attribute, and each of the information sources are modeled as diffusion processes. So all the information are Gaussian. Specifically, these diffusion processes will have drift that is equal to the unknown attribute value, and with a volatility term that is equal to 1 over the square root of the attention level. This is just a normalization to ensure that giving x units of attention to a particular source is equivalent to receiving a normal signal about the attribute with precision level x. So there is constant return in terms of precision to the amount of attention devoted to any source. The decision maker observes the path of these diffusion processes up to the current time, and at some endogenous time will decide to stop and take a decision. Now, ultimately, we assume that the decision maker does not care about the attribute values per se, but rather cares about a single linear combination of them, which I denote by omega. It is the weighted sum of these attribute values with weights that are strictly positive. If the decision maker stops at a particular time tau and takes an action A, the payoff is going to be a general function of the stopping time, the action taken, and the unknown state of the world. We make relatively weak assumptions on this utility function. The only assumption we need is that this utility function is decreasing in the stopping time, so that earlier decisions are always better. So just to add a little bit of formality, in our model, what the decision maker does is to choose an attention allocation strategy, which I am going to denote by capital S, and a stopping time, which I denote by tau, to maximize the expected utility at the time of stopping. Now, when we think about such a problem, we oftentimes in these problems, the optimal attention strategy S and the optimal stopping time tau need to be determined in a joint way. But our results are going to show that under the conditions we provide, the optimal attention strategy S can be characterized independently of the stopping time. And this turns out to be very convenient for some applications. So let me now get into describing the main results in the paper. I'm going to start by discussing the simple case of just two attributes and two sources. In this case, the decision maker wants to learn omega, which is equal to alpha 1 theta 1 plus alpha 2 theta 2, using information about theta 1 or theta 2. I'm going to, for our results to hold, I'm going to need an assumption on the prior belief. And let me just introduce a bit of definition. Here, covariance 1, which is the term that I'm highlighting on the slide right now, denotes the prior covariance between the state, omega, and the first attribute. Similarly, I'm going to define covariance 2. What's the meaning of these covariances? Intuitively, the larger is the covariance, the more information this attribute will give about the payoff relevant state. So the assumption that I need for the result in the k=2 case is that the sum of these prior covariances is non-negative. In other words, this requires the two attributes to be not too negatively correlated in the prior. And this assumption is satisfied in a number of special cases. For example, if the two payoff weights, alpha 1, alpha 2, are equal, or if the prior correlation between the two attributes is positive, or if the prior uncertainty about the two attributes are symmetric. Under this assumption, what we can show is that the optimal attention strategy will proceed in two stages. Up to a certain time t1, the decision maker will focus exclusively on the first attribute, on one of the attributes. Here it's the first attribute because I've made an assumption that the prior covariance, covariance 1 is bigger than covariance 2. After this time t1, however, the decision maker will switch to dividing attention between the two attributes using a constant fraction over time. And notice that this constant fraction is proportional to the payoff weights. So the interpretation of this optimal strategy is that in the first stage, the decision maker should focus on the attribute with greater prior covariance with the state. And the idea is that the marginal value of learning this attribute is initially higher than learning the other attributes. Once sufficient amount of attention has been devoted, however, the marginal values of the two attributes will equalize. And in the long run, which is stage 2, the optimal strategy will divide attention in proportion to the payoff weights. Why is it in proportion to payoff weights? It's because in the long run, the prior shouldn't matter for how to efficiently learn the payoff relevant state. And devoting attention in proportion to payoff weights produces an unbiased signal about the payoff relevant state, which turns out to be the most efficient way of learning. So let me walk you through a couple of examples to illustrate this result. In the first example, we have two attributes that are independently distributed in the prior, but attribute 1 has a larger prior uncertainty, which is 6, compared to 1 for attribute 2. So in this case, because the prior uncertainty about attribute 1 is larger, and because the payoff weights are equal, the decision maker should initially attend to attribute 1. At some time t1, the posterior belief will become the identity matrix. And because of the symmetry in this posterior belief, it is natural that after this time t1, the optimal strategy is to divide attention equally. For a second example, imagine that we modify the previous example by introducing a bit of positive correlation in the prior belief, which is the 2 highlighted in blue here. In this case, again, in stage 1, the decision maker exclusively attends to attribute 1, but at some time, t1 again, the posterior covariance matrix will again be symmetric between the two attributes. The posterior uncertainty of the two attributes are both 3/8. And so for symmetry reasons, after this time t1, it is optimal to divide attention equally. For a third example, we make it a little more complicated by making attribute 2 a little more important in the payoff relevant state. So now attribute 2 is weighted twice as important as attribute 1. In this case, we can compute covariance 1 and covariance 2, these prior covariances. It is still true that attribute 1 has a higher prior covariance. And so stage 1 puts all the attention on learning about attribute 1. At certain time, t1, the agent will switch to dividing attention between the two attributes. And now we notice that the posterior belief at this time t1 is not really symmetric between the two attributes. So after this time t1, it is not actually optimal to devote equal attention to the two attributes, but instead the optimal fraction is in proportion to the payoff weights, which in this example is 1:2. For the interest of time, I'm going to basically gloss over the generalization to more than 2 sources. But a quick summary is that the multi-stage structure of the optimal strategy generalizes. The decision maker initially attends to only one attribute. At some later point, adds another attribute to the observation set, so on and so forth. Let me spend a couple minutes just explaining why the result is true. So for this, we're going to consider a simpler problem where the decision maker always stops at a certain fixed time t. For this problem, because we have normal signals, it is a classic result that normal signals can be ranked in the Blackwell order based on the posterior variances that they induce. So for fixed decision time t, the optimal way to allocate attention will minimize the posterior variance of the state at that decision time. And this is independent of the payoff function. So this motivates us to define the so-called t-optimal attention vector, which is the optimal allocation of t units of attention that would minimize the posterior variance. Now, in our problem, the stopping time is endogenous. So there is a distribution of stopping times. We have to worry about how to connect these different t-optimal attention vectors. If it happens that at some later time t prime, the optimal way of dividing t prime units of attention gives less attention to source I than the optimal way at time t, then these optimal attention vectors for the two fixed times cannot actually be achieved by the same dynamic strategy. Because to achieve this, we would have to take away what we have already devoted to source I at time t. The converse is also true, which is that as these t-optimal attention vectors increase over time in each coordinate, then there will be a strategy that minimizes the posterior variance, not just at time t, but at every time. And we have a lemma in the paper which shows that such a uniformly optimal strategy is in fact also optimal for the endogenous stopping problem. Now the question remains as to under what conditions will these t-optimal vectors increase in time. And this question turns out to relate to a more classic question in consumer demand theory regarding the normality of demand. Because we can think of a consumer whose utility function is the negative of the posterior variance, so that maximizing utility is the same as minimizing posterior variance. With this interpretation in mind, what our condition on the prior belief does is to take advantage of the particular form of our posterior variance function to establish such normality of demand. For the interest of time, I'm just going to skip talking about more details of the optimal strategy, but give a quick summary of the three applications we pursue in the paper. In the first application, we consider a binary choice problem where the decision maker has to choose between two objects with unknown payoffs. Here, we're able to use our characterization to generalize a reasoned result about earlier decision times being more likely to be accurate. In the second application, we study the persistent effects of a one-shot attention manipulation. And what we show is that this effect turns out to depend on whether the information sources are complements or substitutes. And in our last application, we propose and solve a new model of biased media competition where media sources compete for reader attention. And we make some novel predictions about the relationship between news bias and equilibrium quality of reporting. That's the end of the talk. Thank you very much.